Optimizing Apache Spark performance is critical for unlocking faster insights, maximizing resource efficiency, and controlling cloud costs in modern-day platforms. Both Databricks and Microsoft Fabric provide powerful Spark runtimes enriched with native optimizations and integrations tailored to their unique architectures. In this video, we'll deep dive into specific techniques and best practices to improve query speed, boost resource utilization, and reduce your overall operational costs across these platforms. You'll learn about runtime enhancements like adaptive query execution, dynamic partitioning, and file pruning, and native execution engines such as Databricks' Photon and Fabric's native Spark engine. We'll explore advanced data layout strategies like V-ordering and Z-order indexing that enable efficient data skipping, as well as practical operational patterns like vacuuming and clustering to maintain optimal table health. You'll also see how smart cluster management using dynamic allocation and high concurrency configurations ensures your compute resources scale efficiently to workload demands. Additionally, we'll cover custom Spark pool configurations, caching, cost-based query plans, and best practices for join optimization, including broadcast joins and skew handling. Through concrete examples and configuration snippets, this guide will equip you to harness the full power of both Databricks and Microsoft Fabric for your Apache Spark workloads. By the end, you'll have a clear roadmap to accelerate your data pipelines, deliver faster analytics, and gain cost efficiencies on your data modernization journey using these cutting-edge platforms. Performance optimization in Databricks and Microsoft Fabric hinges on 4 key areas: native execution engines, query optimization, data layout, and resource management. Databricks' Photon engine is a native vectorized runtime that accelerates SQL and data frame operations by maximizing CPU parallelism. For example, a large fact table query can be cut down from 15 to 7 minutes simply by enabling Photon with no code changes. Microsoft Fabric's native engine similarly boosts batch Spark jobs transparently. Enabling Photon or using Fabric's Spark pools ensures automatic performance gains. Query optimization techniques like adaptive query execution dynamically adjust query plans during execution. This can reduce runtime by 40% in joins with skewed data by dynamically optimizing join strategies and shuffle partitions. Dynamic partition pruning minimizes the data scanned in star schema joins, reducing a 20-minute query to 8 minutes in one case. Databricks Dynamic File Pruning prunes files inside partitions for further I/O reduction. Effective data layout through V-order and Z-order clustering on Delta Lake tables enhances data skipping. For instance, Z-ordering by customer ID and order date can cut scan data by 50% in sales queries. Regular vacuum and optimize operations maintain table health by cleaning stale files and compacting small files, improving query latency. Resource management features like dynamic allocation scale executors automatically, reducing idle resources and cutting costs, saving up to 25% in multi-user ETL workloads. High concurrency clusters enable efficient multi-tenant usage, while Fabric's customizable Spark pools, including GPU support, accelerate specialized workloads like ML training by 40% in some cases. Tuning pool-specific configs, shuffle partitions, memory overhead, serialization further optimizes performance. By combining these native adaptive query techniques, smart data layouts, and dynamic resource management, you unlock faster queries, greater resource efficiency, and lower cloud costs on Databricks and Microsoft Fabric. Native execution engines are foundational to boosting Apache Spark performance in both Databricks and Microsoft Fabric environments. Let's start with Databricks Photon, a powerful vectorized query engine built to accelerate SQL and data frame operations by fully leveraging CPU parallelism and modern hardware instructions. One of the biggest advantages of Photon is that it requires no code changes. Simply enabling Photon within your Databricks SQL warehouses instantly provides significant speedups to your workloads. For instance, a large fact table query that originally takes around 15 minutes could be cut down to 7 minutes just by enabling Photon. Similarly, Microsoft Fabric's native execution engine transparently accelerates batch Spark queries running in its Spark pools. This means that your Spark workloads in Fabric automatically benefit from the performance boost without any additional configuration. The key action is to ensure Photon is enabled in your Databricks SQL warehouses or that your jobs run within Fabric Spark pools, so you can take advantage of these native runtime enhancements. By doing so, you harness efficient vectorized processing and hardware optimizations that fundamentally improve throughput and reduce query latency on your data workloads. Adaptive query execution is a powerful Spark feature that dynamically optimizes query plans at runtime based on statistics calculated during execution. This allows Spark to adjust its strategies on the fly to better handle varying data sizes and distributions. Key features of AQE include dynamic join strategy selection, where Spark can switch between broadcast and shuffle joins depending on actual data sizes, automatic coalescing or of shuffle partitions to reduce overhead from many small tasks, and skew join optimization that splits large skewed partitions into balanced tasks for more efficient processing. In practice, enabling AQE can yield significant performance improvements. For example, a join query on highly skewed data could see a 40% reduction in execution time by dynamically optimizing join strategies and partitioning during runtime. This runtime optimization makes your Spark jobs more resilient to unpredictable data patterns, reduces shuffle costs, and improves overall resource utilization. Key benefits for scalable, cost-effective data processing. Dynamic Partition Pruning, or DPP, is a powerful Spark optimization that eliminates unnecessary partitions from large fact tables during join execution based on filters applied to dimension tables. This makes it especially effective for star schema queries, where a smaller dimension table filters a much larger fact table. DPP is enabled by default in Spark 3.0 and Databricks Runtime 6.1 and above. It works best when your fact table is partitioned on the join key and the join is an equijoin. By dynamically pruning partitions at runtime, DPP greatly reduces the data scanned, cutting query time significantly. Dynamic File Pruning, or DFP, is a Databricks exclusive enhancement that takes pruning a step further by eliminating unnecessary individual data files within partitions during query execution. This reduces I/O even more than partition pruning alone, benefiting queries on highly partitioned or large tables with many files. DFP requires Photon-enabled compute and is automatically triggered for qualifying workloads. For example, a join between a 5 terabyte fact sales table and a 10 gigabyte dimensions customer table could reduce scanned data by approximately 60% and cut the query runtime from 20 minutes to 8 minutes due to these pruning techniques. So when should you use each one of these? Well, use dynamic partition pruning when you have a star schema join the large fact table is partitioned by the join key, and you want to filter out entire partitions dynamically during execution. This is the more general technique available in Spark and Databricks. You could use Dynamic File Pruning in Databricks environments with Photon Compute for additional efficiency gains by pruning individual files inside these partitions. It really complements DPP, especially on large delta tables with many small files. Both optimizations help significantly reduce data scanned and improve query performance without manual tuning, making them essential tools for efficient Spark query execution on large data sets. Join optimization is a crucial element in enhancing Spark performance, and selecting the right join strategy depends on the size and distribution of your data sets. When you have a small table, joining a much larger one, a broadcast join is highly effective because it avoids costly data shuffles by distributing the smaller table to all executing nodes. This speeds up query execution significantly and reduces resource consumption. For joins involving large tables of comparable size, Spark relies on the sort-merge join. While it reduces shuffling and sorting the data by the join keys, it's a scalable and reliable method for handling big data joins. Beyond join methods, the physical layout of your data plays a vital role in query speeds. Techniques like V-order clustering help organize data across multiple columns, improving multi-dimensional pruning, which means queries filtering on several columns simultaneously are more efficient. Meanwhile, Z-order clustering is particularly powerful in Delta Lake environments. It physically reorganizes data files by selecting columns so that data related to common query predicates are stored close together. This organization dramatically reduces the amount of data Spark needs to scan, often cutting scan sizes by half or more for typical workloads. Knowing when to apply each approach is critical. Broadcast joins work best with small dimension tables. Sort-merge joins suit large datasets. V-order clustering benefits complex multi-column filters, and Z-order clustering enhances performance for frequent predicate-based queries on delta tables. By pairing the right join strategy with intelligent data layout optimization, you can significantly reduce shuffle overhead, minimize scan data, and accelerate your overall query performance in both Databricks and Microsoft Fabric environments. Effective management of Delta Lake tables is critical to maintaining high query performance as your datasets grow. One key practice is using the vacuum command, which removes obsolete and deleted files that Delta no longer needs. This cleanup reduces metadata overhead and prevents your queries from sifting through stale data, which can cause unnecessary delays. Typically, you retain data for a period, commonly 7 days, to balance cleanup with data versioning and recovery needs. Another essential operation is optimize, which compacts many small files into larger ones. Small files can accumulate after frequent data writes and append operations, leading to inefficient reads and increased latency. By compacting these files, Optimize reduces file overhead and improves I/O efficiency. Additionally, Optimize often includes data layout enhancements like Z-ordering, further optimizing query speed. A powerful feature built into Delta Lake is automatic data skipping. This relies on metadata statistics that track min and max values for each data file. When your query filters on certain columns, Spark can skip files that don't contain relevant data, dramatically reducing scan scope and accelerating query execution. In production environments with large partitioned datasets, sometimes containing millions of small files, establishing a regular maintenance schedule of nightly optimize followed by vacuum could consistently deliver up to a 30% improvement in query throughput. This routine keeps your tables lean, your metadata manageable, and your analytics responsive. In summary, regularly applying vacuum to clean up old files, running the optimize to compact and reorganize data, and leveraging Delta's data skipping capabilities are foundational best practices to ensure sustained, high-performance querying on Databricks and Microsoft Fabric. Effective cluster and resource management is essential to running scalable, cost-efficient Spark workloads in Databricks and Microsoft Fabric. One key feature that enables this is dynamic allocation. With dynamic allocation enabled, Spark automatically scales the number of executors up or down depending on the real-time workload demand. This means during periods of heavy data processing, more executors are requested to meet parallelism needs, while during idle or low activity phases, executors are released to save resources and cost. For example, you can configure minimum and maximum executors to set boundaries on scaling, ensuring your cluster never over-provisions or starves resources. In practice, using dynamic allocation in a high-volume ETL environment could lead to about a 25% cost savings by reducing wasted compute during off-peak times and smoothing workload peaks effectively. Complementing this, high concurrency clusters enable multiple users and jobs to share the same cluster efficiently. These clusters provide workload isolation, session management, and fair resource scheduling, making them ideal for environments where many teams or workloads run concurrently, such as shared ETL pipelines or interactive data exploration. Monitoring executor scaling through tools like Spark UI is vital to understanding how your cluster adapts and to fine-tune settings for optimal performance and cost balance. In summary, enabling dynamic allocation alongside high concurrency clusters allows you to efficiently right-size your Spark resources, handle mixed workloads gracefully, and reduce cloud infrastructure costs without sacrificing performance. Beyond the core Spark optimizations, there are several advanced tuning techniques that can further boost your workload performance. First, tuning the number of shuffle partitions is crucial. Spark's default shuffle partition count is 200, which may not be ideal for all workloads. Increasing this to a number that better matches your data size and cluster capacity, such as 500, can improve parallelism and reduce task skew, leading to faster overall query execution. Next, the cost-based optimizer, or CBO, plays a vital role in query planning. By collecting detailed statistics on your tables, such as data distribution and cardinality, via commands like analyze table, Spark can make smarter decisions about join orders and data movement. This can significantly reduce query times in practice, collecting statistics that could cut down some join runtimes by as much as 35%. Another useful approach is providing explicit broadcast hints in your code when you know a table is small enough to be broadcast. This guides Spark to avoid expensive shuffle joins by replicating small datasets across executors, improving join efficiency. Caching intermediate data frames or datasets is also a highly effective way to speed up iterative workloads, especially in ML pipelines or repeated queries. By caching data in memory, you avoid recomputing expensive transformations. This method has been shown to improve iterative pipeline speed by 20% or more. Finally, handling data skew is critical for avoiding bottlenecks. Techniques like data salting, adding a random distribution key, or relying on Spark's adaptive query execution skew join capabilities helps distribute work evenly and prevent straggler tasks from slowing down your jobs. Together, these tuning strategies complement core optimizations, enabling you to fine-tune Spark workloads for improved efficiency, stability, and speed, especially in complex or large-scale pipelines. To wrap up, the key to maximizing Apache Spark performance in both Databricks and Microsoft Fabric lies in thoughtfully combining several core techniques. Adaptive query execution dynamically optimizes your queries during runtime, while dynamic partitioning and file pruning minimize unnecessary data scans. Data layout strategies like Z-order clustering significantly reduce the amount of data read, and regularly vacuuming and optimizing operations keep your delta tables performant and lean. On the resource side, dynamic allocation ensures your cluster scales in response to workload demands, helping balance cost and performance. Caching immediate results further accelerates iterative workloads and repetitive queries. However, optimization is an ongoing process. Continuously monitor your workloads using tools such as the Spark UI, Databricks Jobs UI, and Fabric monitoring dashboards. Use these insights to iteratively fine-tune your configurations and resource settings. Importantly, balance performance improvements with cloud cost management by right-sizing clusters and leveraging auto-scaling features. Finally, foster a culture of knowledge sharing across teams. By spreading these best practices, you empower your organization to build scalable, cost-effective, and high-performing data analytics pipelines